Lighthouse Scientific Education presents a lecture in the Chemical Reaction series. The topic: Types of Chemical Reactions. Material in this lecture relies on an understanding of the previous lectures, order and matter, and bonding, an overview. Leading the lecture is a review of indicators of a chemical reaction. Then it is on to an introduction of the 5 types of chemical reactions, followed by more thorough descriptions of the 5 types of chemical reactions. Offered along the way and then summed up together are general tips or keys for identifying types of chemical reactions, which are put to use in a quiz. First, to indicators of a chemical reaction. First and foremost, not all chemical reactions have observable changes. Observable, in this context, is observable by the 5 senses. Observable changes include a change in color or odor, the formation of a gas, up arrow indicates escaping gas, or a solid or precipitant, down arrow indicating a sinking solid. The shorthand for precipitation is PPT. Also, there is the release or absorption of energy as heat. The Greek symbol delta is the most common symbol in chemistry to indicate a change in heat. And then there is the release or absorption of energy as light. Light can be indicated in a chemical reaction by writing its energy equivalent H nu or by adding a cartoon bolt. A caution before we proceed. Textbooks vary on the names and the number of common chemical reactions. That is, some lists of common reaction types group particular reactions together, and some list them separate into their own category. The following list is therefore to be taken as a general list. Commonly, the synthesis reaction is the first to be listed. Such reactions follow the pattern chemical A reacts with chemical B to form chemical AB. Sometimes this reaction is also called an addition or combination reaction. The reverse of the synthesis reaction is the decomposition reaction. These follow the form of chemical AB breaking down to yield chemical A and chemical B. And then there is the single displacement reaction. Here chemical A reacts with chemical BC to produce chemical AC and chemical B. Chemical B in this reaction is replaced with chemical A. Compare that with the double displacement reaction. Chemical AB reacts with chemical CD to produce chemical AD along with chemical CB. In these reactions, there is a partner swap in the compounds. Quick note, some textbooks use the term replacement for the term displacement. A subset of this reaction, and one that is often broken down into its own category, is called the neutralization reaction. Here, an acid, proton donor, reacts with a base, most often the hydroxide ion, to form a salt and water, H2O. The last type of reaction is called oxidation-reduction. These reactions are generally given their own section of study. We will limit our discussion to one important family of the oxidation-reduction reactions. That is the combustion reaction. Chemical AB, often an organic chemical, reacts with molecular oxygen to produce CO2 and H2O. That is our cast of characters. Each will be discussed in some detail, beginning with the synthesis or addition or combination reaction. Chemical A reacts with chemical B to form chemical AB. Using the terminology of the chemical equation, 2 reactants combine to form a single compound, which is known as the product. While the terms chemical and compound are frequently used in describing this reaction, it will also contain elements. As mentioned, this reaction goes by other names, including combination or addition reaction. All 3 names reflect the nature of the reaction. A couple smaller chemicals combine or add to synthesize a new larger compound. The key or tip to recognizing synthesis reaction is that it only has one product. Some examples are in order. Beginning with an equation for the formation of water. It starts with 2 hydrogen molecules reacting with 1 molecular oxygen molecule. In a real reaction, we would have used moles instead of molecules, But here we will stay with molecules so that we can bring in a cartoon representation of the reaction at the molecular level. It shows all of the reactant atoms in their appropriate compounds. There are 4 hydrogen atoms and 2 oxygen atoms. The synthesis product is 2 water molecules. Its cartoon representation shows the same 4 hydrogens and 2 oxygens, but arranged in a different molecular pattern. Reactants are combined to form a product. Saying a product does not mean that the product will have a coefficient of 1, but rather there will be one kind of compound. Another synthesis reaction is the formation of ammonia. It requires 3 H2 molecules and 1 nitrogen molecule. The synthesis is 2 ammonia molecules, which are the combination of the reactants. The hallmark of this reaction is a single product. The coefficient 2 is the count of that one type of molecule. Perhaps the term compound should be used instead of molecule, since it is actually a more inclusive term. It also includes the formation of ionic compounds. For example, sodium atoms interact with a chloride molecule to form 2 sodium chlorides. NaCl is the formula unit for the salt. Note that the atoms have become ions and are arranged in the matter to maximize attraction and minimize repulsion. The next type of reaction is the decomposition reaction. Chemical AB breaks down to form chemical A and chemical B. As a reaction, it is identified as a single compound that breaks down into 2 or more products. It is a complex compound breaking down into simpler products. Often the breakdown is in elements, and as can be seen, it is the opposite of the synthesis reaction. The key or tip to recognizing decomposition reactions is that they have only one reactant, as is the case for the decomposition of water. 2 H2O molecules decompose into 2 hydrogen molecules and 1 molecular oxygen. The cartoon clearly shows that the hydrogens and the oxygens are separated into their own compounds. They are no longer combined. Indeed, the decomposition reaction of water is the synthesis reaction, but shown in the opposite direction. Another decomposition reaction involves 2 mercury 2 oxide molecules. The compound is a solid at room temperature and consists of a mercury bonded to an oxygen. When heated to 500 degrees Celsius, note the delta symbol above the arrow, it decomposes into 2 mercury atoms and 1 molecular oxygen. Both are in the gaseous form. The single reactant breaks down into its elements. And then there is the base calcium hydroxide. It is the ionic compound known as slacklime. When heated, it can decompose into compounds calcium oxide and H2O. The high temperature of the reaction means that the water is found in the gaseous state. Unlike the previous examples, these products are not in their elemental form. Notice that there is an oxygen in the calcium oxide and in the water. The decomposition reaction does not require the elements to be separated into different compounds. This example is better described as a more complex compound breaking down into simpler compounds. The hallmark of the decomposition reaction is a single reactant. The third type of reaction is called the single displacement reaction. Chemical A reacts with chemical BC to produce chemical AC and chemical B. From the perspective of a chemical reaction, this is where one element replaces another element in a compound. Chemical A replaces chemical B in the compound BC and forms the compound AC. This reaction can also be called a single replacement, a precipitation, or a substitution reaction. Often ions and elements are involved. For the displacement, a metal usually replaces a metal, or a nonmetal replaces a nonmetal. That is, chemical A and chemical B are either both metals or both nonmetals. The key or tip to distinguishing a single displacement reaction is that on the reactant side, there is a single free element that replaces an element in a compound. Single free just means that the element is not in a compound with another element. It can be in a molecule like O2 or N2, that is, it can be bound with its own kind. One final note, chemical B on the product side does not have to be in an elemental form, as shown in the equation. It too can be in a compound. On to a few examples, and starting with a reaction of elemental copper with silver nitrate. This reaction occurs in water as noted by the AQ subscript. Silver nitrate readily dissolves in water into silver ions and the polyatomic anion nitrate. It is drawn here in its ionic compound form for convenience. This single displacement reaction has the silver in the silver nitrate replaced with copper. The silver is no longer an ion, it is in its elemental state. Silver is the B in the generic equation, and copper is the A. This is a single displacement reaction because copper, as a reactant, is a single free element that replaces the element silver in a compound. Here is a displacement reaction involving methane, CH4. Methane and the diatomic molecule chlorine are gases at room temperature. They react to form chloromethane and HCl. In this reaction, one of the hydrogens on the methane is the generic chemical B, displaced by a chlorine, generic chemical A. This is a single displacement reaction because in the reactants, chlorine is a single free element that replaces the element hydrogen in a compound. It is a bit more difficult to distinguish as single displacement reaction because the chlorine is a molecule and there are still hydrogens bound to the AC compound in the products. Nevertheless, the reaction does meet the criteria even if it has more going on. The fourth type of chemical reaction is a double displacement reaction. Chemical AB reacts with chemical CD to produce chemical AD along with chemical CB. Generally, these reactions occur in an aqueous solution. The cations and anions of two compounds swap places to form new compounds. This reaction is also known as a double replacement reaction. In many of these reactions, one or more compounds may precipitate and sink to the bottom of the reaction vessel. The keys or tips to identifying a double displacement reaction is that all the compounds are usually ionic compounds. Not always. Furthermore, some of the compounds may be accompanied by an aqueous subscript. Also, an inspection of the equation shows that the anions have swapped cations. A special subtype is the acid-base reaction with its distinguishing features. As for examples, we'll start out with using silver nitrate reacting with sodium chloride. The reaction occurs in water as noted by the aqueous subscripts on the compounds. Both silver nitrate and sodium chloride are ionic compounds that dissolve completely in water. As such, the aqueous solution contains solvated cations, silver and sodium, and solvated anions, nitrate and chloride. Solvated means that there is a shell of water molecules around the ion. While the silver cation is still attracted to the nitrate anion, they do not reform into a compound in water. That cannot be said for the attraction of silver cation for chloride anion. These oppositely charged particles attract and form a compound, a solid. Silver chloride is the product of the reaction and precipitates out of solution. The sodium cation and nitrate anion are also attracted, but not enough to form a compound. They stay as dissolved ions in solution, as is noted with the aqueous subscript. Double displacement does not actually require that both products form stable compounds. At least one of the products has to form a stable compound. If mixing two ionic compounds in water does not produce a new compound, then there isn't a displacement reaction. A second and very common example of a double displacement reaction is the mixing of sodium sulfate and barium chloride in water. Both of these ionic compounds readily dissolve in water, forming solvated cations and anions. A double displacement reaction occurs when the solvated cation from one compound, barium, is attracted to and binds the solvated anion of the other compound, sulfate. These swap pairs form the stable compound, barium sulfate. Barium sulfate is an odorless white powder which precipitates out of solution. This can be noted with a down pointing arrow, or as done here, with the subscript S for solid. The other cation and anion pairing produces sodium chloride, which of course is dissolved in water. All the hallmarks of the double displacement reaction are here. All ionic compounds, the aqueous subscripts, and swapped partners. There is a subset of double displacement reactions that sometimes get their own category. It is the neutralization reaction. For the most part, it takes place in water. The reactants are an acid, as defined by the donation of a hydrogen ion, and a base, limited to those containing a hydroxide ion, OH-. The products are a salt and water. It is a very special kind of double displacement reaction. Consider the reaction of sulfuric acid and the base, sodium hydroxide. The aqueous subscripts on the reactants indicate that the reaction takes place in water. Sulfuric acid is a strong acid, and sodium hydroxide is a strong base. Both the acid and the base are ionic compounds that readily dissolve in water, hence the description strong. Neutralization means that the acid and base properties have been destroyed or neutralized. That can be seen with the products of the reaction. Sodium sulfate is a salt, and H2O water, the compound. Salt water is considered neutral. The same argument with the equation can be made in which the cation from the first compound is attracted to the anion of the second compound, forming a new compound. Additionally, the cation of the second compound is attracted to the anion of the first compound, forming a new compound. This compound is soluble in water, and the sodium and the sulfate are found as solvated ions. It is the formation of water which drives this reaction. Precipitation of a product is not required, only the formation of a stable compound, and water holds that role in this reaction. The last of the reaction types covered in this lecture is the Oxidation-Reduction Reactions. These reactions are one in which an element loses an electron or electrons, and another element gains those electron or electrons. Important terminology includes oxidation. That is the part of the reaction dealing with the loss of the electron. And then there is reduction. It is the part of the reaction that deals with the gain of electrons. There is sometimes confusion with the pairing of the terms reduction and gain. What reduction refers to is the reduction of net charge on the element that gained an electron. Since electrons are negatively charged, adding electrons is adding negative charge. That reduces or lowers the net charge on that element. An analogy would be gaining a bill for some product. The bill is gained, but one's money is reduced. A helpful anacronym in remembering the connection between oxidation reduction and loss gain is oil rig. It is the first letter of each word in oxidation is lose and reduction is gain. There are other such tricks, but this one will do nicely. The thing to remember about oxidation and reduction is that they have to happen together. There is no gain without loss. There is no loss without gain. The electron is transferred. The reaction name shortens down into redox. An oxidation-reduction reaction is a redox reaction. Many reactions involve the transfer of electrons. Therefore, redox reactions are also found under other reaction classifications. For example, synthesis and single displacement reaction can often involve electron transfer. Redox reactions can be quite involved. In fact, it is a topic unto itself. As such, it is given its own coverage later in most chemistry courses. There is one specific type of redox reaction that does get covered in the study of reaction types. It is the combustion reaction. Chemical AB, often an organic chemical, reacts with oxygen to produce CO2 and H2O. The hallmark of a combustion reaction is when a compound or element reacts with oxygen to release heat or energy and produces an oxide. In this reaction shown here, the oxide is carbon dioxide. There are many reactions that fit this definition of combustion. The one we are most familiar with, and the one that produces the energy our body uses, is hydrocarbon combustion. The general equation for combustion can be further refined by replacing AB with a generic compound containing carbons and hydrogens, a hydrocarbon. Many naturally occurring hydrocarbons also include the element oxygen, so an oxygen could have been included too. We know hydrocarbon combustion by its more common name of burning or fire. Fire requires a fuel, a hydrocarbon, oxygen, and heat. And its products always include carbon dioxide and water. Therefore, the key to identifying a hydrocarbon combustion reaction is that it will always have molecular oxygen as a reactant and carbon dioxide and water as products. A few examples should give us some perspective as how ubiquitous or how prevalent the hydrocarbon combustion reactions really are, including the burning of methane. Methane is found in natural gas and is used for home heating. The family barbecue might have a tank of propane to provide the hydrocarbon fuel. Oxygen is taken right out of the air. And then there is the reaction that lies at the heart of life on our planet, the metabolism of glucose. Glucose, C6H12O6, is the hydrocarbon that, when combined with oxygen from breathing, produces the energy that powers our cells, and produces the waste products, carbon dioxide and water, which we breathe out. And that ends the survey of the basic reaction types. It is one thing for the student to be shown a reaction and to follow the description of its reaction type. It is another thing for the student to be given a reaction and to be able to identify the reaction type. The rest of the lecture is given over to that objective. It starts by gathering the keys or tips for identifying reaction types. Here are the reaction types covered in this lecture. Viewing them together can help build the pattern that leads to correct identification. The overarching tip is to identify reactants and products as either compounds, that is, covalent or ionic, or as elemental. Remember that diatomic molecules like O2 and N2 are considered elemental forms. This level of classification is exploited in the following tips. Synthesis reactions have only one product. Compare this with decomposition reactions. They have only one reactant. These two types of reactions should be relatively easy to spot. Single displacement reactions have a single free element in the reactant that replaces an element in a compound. Double displacement reactions usually have all ionic compounds. Additionally, look for the subscript AQ, since swapping of cations and anions will usually take place while they are dissolved in water. A particular kind of double displacement reaction is an acid-base neutralization reaction. Look for an acid and a base in the reactants and a salt and water in the products. And then there is the redox reactions, which we limited to just combustion reactions. These will have oxygen, O2, as a reactant and CO2 and H2O as products. Using these tips, let's put our newfound understanding of reaction types to the test with a little quiz. Consider the reaction of magnesium hydroxide in hydrochloric acid. It produces magnesium chloride and water. There are two general approaches to identifying reaction types based on a list of types. The first is to spot a telltale sign based on the tips we covered. The second is a process of elimination. What reaction type is this reaction not? A run through our tips excludes synthesis and decomposition because there are more than one reactant and one product. There is no free element in the reactant, so single replacement is out. Combustion is out because there's no molecular oxygen in the reactants. Okay, well then, what is there in this reaction? In the reactants, there are two ionic compounds, magnesium hydroxide and hydrochloric acid. That's a start. We also note that the reaction takes place in water by the aqueous subscripts on the acid. Furthermore, magnesium hydroxide is a base because it contains the hydroxide ion. Looking at the reaction as a whole, the cation of the second compound is attracted to the anion of the first compound to form an ionic compound in the products. Stable product, water. And then there is the cation of the first compound being attracted to the anion of the second compound, forming a salt in the aqueous form. Taken all together, this must be a double displacement reaction. Furthermore, if we return to some of our earlier observations, we would notice that the reactants are an acid and a base, and the products are salt and water. So this reaction can also be categorized as a neutralization reaction. This is probably as involved of a reaction that the student will come across. The next reaction has solid potassium being added to liquid water to produce a soluble salt, potassium hydroxide, and the gas, hydrogen. Again, the absence of a single reactant or product eliminates synthesis and decomposition reactions. That the reactants are not ionic compounds indicates that this is not a double displacement reaction. A key, though, is that one of the reactants is an element, a free element. Furthermore, it can be seen that one of the hydrogens in water is replaced with potassium in the products. That makes this a single displacement reaction. The next reaction has a recognizable pattern. It has oxygen as a reactant and carbon dioxide and water as a product. This distinct reaction is, of course, a combustion reaction. These reactions should become relatively familiar to the student relatively quickly. The fourth reaction has tetraphosphorus or white phosphorus reacting with molecular oxygen to form diphosphorus pentaoxide. None of these compounds are ionic. There is a free element on the reactant side, but nothing is replaced. One of the reactants is molecular oxygen, but the products do not contain CO2 and water. The driving feature, however, is a single product, and that is a tip for synthesis or addition reactions. To be fair, this reaction could fall under the redox umbrella, but given our current level of study, it is better suited for synthesis. The final reaction has iron 2 carbonate becoming iron 2 oxide and carbon dioxide. This one only has one reactant, and it looks like it is breaking down. The only reaction type we've come across with these parameters is decomposition. With these 5 problems, we have reviewed the thinking that goes with identifying reaction type. There is some elimination and some tip recognition. Remember, the tips and this aspect of chemistry should be all yours. Recapping the lecture. Not all chemical reactions have observable changes. Some do, though. Such changes include changes in color or production of an odor, the formation of a gas or a solid, and the release or absorption of heat or light. 5 major types of reactions were covered in this lecture, beginning with the synthesis or addition reaction. A reacts with B to produce AB. This reaction can be assigned by noting that it has only one product. The opposite of this reaction is the decomposition reaction. AB decomposes to produce A plus B. Often heat is involved to facilitate the decomposition. These reactions generally only have one reactant. In a single displacement reaction, A reacts with BC to produce AC along with B. These reactions are noted by having a single free element that replaces an element in a compound. For the double displacement reaction, AB reacts with CD to produce AD along with CB. The reactants are generally all ionic compounds. Additional clues are the AQ subscripts and the swapping of cations and anions. A subset of these reactions is the acid and base neutralization. Products are a salt and water. The final reaction type is the Oxidation-Reduction Reaction, or redox. We only covered one subtype, and that was the combustion. AB reacts with oxygen to produce CO2 plus H2O. Having molecular oxygen as a reactant and CO2 and H2O as products are the hallmark of this reaction. And that concludes the lecture on reaction type. When handling reactions, consider all aspects of the chemical equation. Blend your foundation with new learning.